So some important pieces for this lesson that we're going to talk about is electric flux. We need to remember that cos of 0 is 1, cos of 90 is 0, and cos of 180 is minus 1. You can check that in your calculators yourself. Make sure your calculator is on degrees. So we're going to understand electric flux, do some example problems, and explore various situations in which flux is present. So the title for this lesson will be electric flux. Moving on. What is electric flux? First of all, we know it's a number of field lines passing through an area perpendicularly. So if I have an area here like this, and what I do is I place it in front of a bunch of field lines, any field that cuts through here is part of the flux. That's it. That's what flux is. It's a number of lines. I will count all of these lines across this area. So if I have a bigger area, I will catch more lines. If I have more lines, I will have a bigger flux. Both ways will give you a bigger flux. Okay, so we know that more lines means more flux. More space to catch the lines, more flux. We came up with the formula flux equals EA, and this is when this is perpendicular. This is the area vector pointing outwards, otherwise known as the normal. If you remember the normal, it's pointing out of a flat plane. So if I was to have a plane pointing like this, yeah, let's say this is pointing upwards, and that means it has a normal going up in this direction. My area vector is pointing like this. Now I can introduce a field line going up, and you can see that they're pointing in the same direction. It's perpendicular to the surface, but it's pointing in the same direction as a normal. That means here the angle is taken from. In this case, there is no angle, cos of 0. Okay, and if you remember cos of 0, that is 1. So you don't need to write it. It'll just be EA cos of 0, EA 1, just EA. Otherwise, when the angle changes, if I was to have a field going like this at a little angle, you take the angle from the normal. Here is we have a little angle, this one right here, and you can calculate that. It could be anything. Let's say it's 30 degrees. EA cos of 30. That's what we will do. And that takes us to the rule, dot product being EA cos of 30. And also, by the way, FYI, if it's perpendicular, 90 degrees, so that means if this case, this is fine because this is angled slightly. We have this right here, and we need this angle from the field line. That's great. But if it was perpendicular, if it was like this was my surface, and look, my field lines are going to the right. You can see straight away it's not catching any lines at all. They're just passing through it. And the reason it's 0 is because this becomes a right angle. This becomes cos of 90. We know that cos of 90 is simply 0. That's why there is nothing going on. We calculated some problems. We solved some of these here in class. And then we looked at something a bit more challenging, which was a cube. We have an electric field. Let's say it's traveling to the right. And there are 3 questions. Which faces will it be 0? And can you write an expression for the faces? And finally, what will the overall flux be? First of all, remember, it has to catch the lines. The only ones that are catching these lines are the ones that it's crossing the face of, which is the left side over here and the right side, all of this. If you look at the top, it's just passing over the top. This is perpendicular. The normal is pointing out the way, 90 degrees. This one here, this face is pointing in this direction, which will be 90 degrees as well. Same with the other side, same with the below. So everything around it, these 4 faces, nothing. Only the left and the right. To make an expression for the flux, well, this one here is the face going towards the left. This face is going towards the right. That's great. So for the first one, we can say the flux equals negative EA. And for the second one, we can say the flux is simply EA. And it's positive because it's in the same direction. And the overall flux, well, you add these together. Minus EA plus EA equals to 0. They cancel. The overall flux in this cube is simply 0. Okay. Then I showed you enclosed surfaces. We're going to head over to Gauss's law soon, and this is to do with enclosed surfaces. So what happens now is you use the same idea that I just talked about. We have A, B, C, and D. And if I take one of these surfaces and I just draw a little outline of it, this one I'm looking at is B. The field lines, if it's coming out like that, then fine. This is EA cos of 0. EA cos of 0. EA cos of 0. So they will have a value. There will be something. Nothing cancels. It will not be 0. Okay, the whole thing will not be 0 because EA cos of 0 will give you some sort of number. Looking at another option, for example, C, you can look at the other two yourself based on what we've just discussed. Looking at C, what happens here? This is outside this surface, goes through it, cuts in. This is normal, it's facing that way. This is -1. Yes? Cos of 180 degrees is -1 because the angle here is 180 degrees. And it comes out this side. And of course the normal is facing this direction, so this is +1. Yeah, EA cos of 0 is 1. These two cancel. That becomes 0. And no matter which way I do it, this will be -1, this will be +1. It doesn't have to be exactly minus. Whatever this is, this will be the opposite of that. So you'll end up cancelling each other out no matter which way you're going. So that means if the charge is outside of my enclosed area, the flux is 0. If the charge is inside the enclosed area, then there is a flux. Okay, that is really important to know. And then we did some more examples. We talked about any random shape. It does not matter about the shape. It's going to cut in and out. In and out. -1, +1. -1 and +1. And that will do. We left this as an exit ticket, but we'll leave it there. Thank you.